Okay, so yeah, we covered this sort of the center volume and extents for all of the cells. And one of the things you can do from this extents, which is sort of the next logical step for this, is to make bounding boxes out of it. And so you can take the sort of upper and lower boundaries there, and instead of showing it as a line in the middle, you show it as a box around the object. And this is the much more common representation for these sort of extents. And it also gives you a better idea of how well these extents match up to that given object. And so a lot of metrics that you see commonly in image processing papers involve this sort of bounding box approach because it gives you an idea of how rectangular your object is, so you can see how well it's filling this bounding box. So if it's an object like this, it's filling it quite well, and an object, like this one is filling it quite poorly because it's got this little piece off that causes it to not fit. You can then sort these boxes by sort of anisotropy and show sort of what are the most anisotropic boxes here and the least anisotropic boxes up there. The problem is that it's not a very good match for the objects that you have, and so you want to kind of come up with better approaches for doing this. And so one of the approaches that I mentioned before was that you kind of orient the box, and so you rotate the box around until you have the least amount of empty space. And so that will then give you kind of the best fit for your data. It also gives you an orientation for your object, because the orientation where the box has the least empty space is probably the primary orientation for your object. You can assume your object is sort of an ellipse or a circle or a triangle or one of those objects, and you can do a curve fitting or an optimization to find the object. So you can just sort of say, an ellipse has a minor axis, a major axis, and some rotation, and then you try to optimize those parameters so that it fits your object well. You can also sort of ignore the height and width and those other parameters, and you can focus on more general characteristics like curvature and thickness. And those will be some of the things we talk about in the more advanced object analysis next lecture. Cool. So now we'll talk about principal component analysis. And so since many of you are familiar with this, we won't spend too much time on these slides. But I think it's a very useful tool outside of image processing as well. And it was probably covered in your linear algebra or statistics courses, but at least the courses that I had when I took them were usually pretty terrible, and I had no idea how to actually apply the tools that they were teaching afterwards or what it was useful for. I mean, I could calculate the eigenvalues and eigenvectors of a matrix, but I couldn't actually say what these eigenvalues meant or apply them to real problems. And so principal component analysis is really built off of this eigenvalue analysis, but principal components is sort of a specific use case for it. And that basically what you try to do is it's similar to k-means where it's kind of blind. You just feed in your data and it gives you some sort of output. So unlike k-means, you don't give it a number of groups. You just feed it in, and what it does is it tries to find the orthogonal components that represent your data well. And so if you were to try to look at this example of, you have a curve with time, these are, stock prices, or in this case, the price of a chicken and the price of corn. And you kind of see these plots and you see that they're somehow related, then you'd kind of want to understand, well, how are these components connected together and how can I make the system sort of easier to understand? And what you can do is you can do principal component analysis on this data set and break it down into two components. And what this shows you then are sort of this component here and this component there. And what the first component shows are sort of the overlaps or similarities between chicken price and corn price. And the next component shows you the things that are sort of different between corn price and chicken price. And so, of course, with this example, there's just two objects, and so there's just two classes. And so it's fairly simple to perform yourself. Where this is really helpful is where you have sort of hundreds of different classes, and you want to see sort of what are the underlying forces causing this to change. And so if you see, this curve is sort of the one that contributes to both chicken price and corn price. And so maybe this one's related to weather or the cost of petrol or any number of these other parameters. And so it basically, instead of having a system where you have these two random curves, you get curves that you know are independent of one another, and they're organized by the ones that explain the most variance in your system. And so rather than having to use all of the dimensionality, you can represent most of the changes you see with just the first or the first few components. And so we can plot them again, and you can plot each one of these points as sort of a principal component 1 on the x-axis, and then the price on the y-axis. And so what we see here is that the principal component 1 is sort of correlated very well with the price in both of these samples. And so that's explaining most of the variance we see in the system. Principal component 2 here then doesn't correlate with the price itself very well, that these values are then sort of random, but it correlates with this difference very well. And so this is then explaining the difference between corn and chicken, and this one's explaining sort of the overall price. And so this one might be like the cost of antibiotics, and this one would be the cost of petrol, or something along those lines. And so it gives you the ability to sort of break apart your system into components that are fewer than the number of original data or components you have in most cases. And they explain the variance in sort of a more clever way, so that you're able to see that through the first few, what most of the data is represented by. So we can apply this as well to these shapes that we had before. And so we have x and y values for these points, and we have a huge list of them. And so we can look at the x components and the y components, and then we can do a principal component analysis on this system. And we sort of get the scores, which are eigenvalues, and the components, which are eigenvectors. And so here we show the first score as this green line, and this has then a value of 3.3 and is oriented in that direction. We then have the second score, which is this pink line, which has a value of 1.4 and is oriented in this direction. And so basically what it tells us is that the primary orientation of this object is this direction, without having to assume any model or any, we don't assume it's a square or a triangle or a bounding box. We just put all the points in. And it gives us a length for this dimension. And so it gives you a representation for your system where the first component, so here we show it as x, represents most of the variance in your system. So for many objects that you're trying to analyze, this is then a very helpful representation to have. And then the second represents the second most variance in your system, and the third represents the third most variance in your system. And so actually for images it works quite well, because one of the requirements you have for principal component analysis is that the systems are orthogonal. And so in coordinate systems, you always also want an orthogonal coordinate system, because having anything other than that wouldn't really make sense and wouldn't allow you to kind of reach all the points in your system. And so this actually fits very well and gives us information about how the object is rotated and the size of the object, independent of any model that we try to put in. Is that mostly clear? And so if we look at how this was actually calculated, the first step is to calculate the covariance of all the points that we have in our system. And so here you just calculate sort of the, x, y, xy, xz for all of them. And these then all represent sort of with the center of mass or center of volume subtracted from the image. So this COV does not mean center of volume, this means covariance. COV we did before means center of volume. It's a bit confusing. And then you do this eigentransform on this covariance matrix. And so what you're able to get out are these eigenvectors and eigenvalues. And so what you see is that your covariance matrix can be decomposed into these two different matrices that then tell you about your system and have this sort of orthogonality to them. So kind of the main point of this is that it gives you information on the orientation and the length based just on the points in the image. And so it doesn't require any model, which is very useful. These ones, the first ones, or the values themselves, are listed by the ones with largest variance. And so you know that the first component is the most relevant for explaining your system. And so if you had to make a very simple approximation of your data, you could represent it by just looking at the first or the first and the second component. It gives us the ability to measure orientation in a very reliable way. You don't have to check a bunch of different boxes and see which one has a minimal area, which can be quite time consuming. And they're implemented in very efficient ways. And so one of the nice things about principal component analysis is because it's used in so many different fields, you can use it on really large data sets. And so you can calculate principal component analysis on 10 billion points in order to get a much simpler representation of it. And so, if you look at these other approaches, if you try to do that for 10 billion points, you would easily crash your computer. But for approaches like this, it scales well. What's also nice is that we can then take this principal component analysis and visualize it fairly easily. So this is sort of called the elliptical or ellipsoidal model in 2D and 3D. And what you can take is you can take this tensor that you've sort of extracted, the shape tensor we call it, and represent it as an ellipse. And so what would an ellipse look like that had the same shape tensor as the object we looked at? And so here you've got to take the center of volume that you had before, and then you are able to calculate the lengths of the semi-axes for your ellipse by using this simple formula. And the derivation is very similar to this inertial tensor for ellipsoids, for those of you that come from sort of mechanical engineering. And we see that this ellipsoid model is a much better approximation for the data sets that we're looking at, particularly for an object like this, than the bounding box would have been. You can also get extents, anisotropy, and all of these other metrics from this ellipse model directly. So now we can show what the elliptical model looks like for all these systems, and we can see that for these ones where it had problems before, that it does a much better job of fitting the ellipse to it and representing the object well. So these things like orientation and anisotropy are now much more reflective of the objects rather than the point distribution. And so if we look at sort of what information we are able to get from the bounding box compared to the elliptical model, we can see sort of the lost information quite easily here. And so this is the anisotropy we calculate in the elliptical model, and this is the anisotropy that we calculate in the bounding box model. And so if the bounding box model was just as good as the elliptical model, this would be a perfectly straight line. An r squared equal to 1. But since it's not perfect, we see that there's a whole number of a whole lot of points here that look like they're isotropic, so on this left side, but they actually have an anisotropy. And so all of this are sort of the lost information points. So the bounding box doesn't represent the system very well. And so for all of these objects, the bounding box approach would tell you it's perfectly circular, and in fact, it's not. And so, bounding box might be easier to implement or easier to get out, or some tools only do bounding box analysis. And so if you're using those tools, then maybe you don't have the opportunity to do something more complicated. And this lets you kind of see how much of your data is actually disappearing or how mismatched your analysis is to what you're trying to get out. You can then visualize these objects quite well, where this analysis didn't work, and sort of see, are they in fact anisotropic, and you can see for many of them that they are, and it's just that they were rotated at 45 or sort of a non-zero or 90-degree rotation, which caused the bounding box to be a very poor approximation for what they were. One of the other things that's important to note with this is that a lot of times if you have a system where everything's oriented along sort of the direction that your imaging frame is taking place, so if you have a bunch of vertical cells, that the bounding box gives you a very good approximation when everything's oriented perfectly, but as soon as you rotate your camera or something gets shifted a little bit, then the bounding box approximation gets very bad. And so if you're trying to make a system that's not very sensitive to orientations or alignment of all of the camera optical table components and everything else, then using the ellipsoidal model makes this value much less sensitive to that original orientation. And so in many cases, even if it seems in the beginning like you don't need it, if you sort of take down your setup and build it up again and it has a slightly different orientation, using a bounding box model might give you completely different results, where the elliptical model tends to be much more stable when slight shifts like this happen. Of course, all of these analyses work as well for 3D objects. And so here we have a 3D representation of an ellipse, where you can look at it either as this 3D rendering or as a series of 2D slices. And so here we show a slice at each point in the image. And we want to calculate anisotropy or these other parameters on it. And so how can we do that? And so what we see is that the anisotropy that we had in 2D doesn't fit perfectly to 3D. And can anyone think of why? Or have any guesses why? So if you think about how you stretch out an object in 2D, is there more freedom or different ways you can stretch out an object in 3D? Sort of what's more isotropic? A pancake or anisotropic? A pancake or a plate or a pencil? So what you have in 3D that you don't have in 2D is sort of this extra dimension. And so when you think about a pancake or you think about a pencil, a pancake is large in 2 dimensions and very small in 1 dimension. And a pencil is large in 1 dimension and very small in 2 dimensions. And so that basically you have this 3rd dimension that comes in that isn't accounted for at all by the anisotropy. That all the anisotropy looks at are what are the biggest one, what's the biggest one, and what's the smallest one. And so if you calculate anisotropy, it won't tell you anything about if your object looks more like a pencil or looks more like a pancake. It will simply say that it's not a sphere. And so for looking at objects like cells, this can be quite important because a red blood cell looks more like a pancake. And if it looks very, very round or it's completely spherical, then this is a bad sign. This means maybe it's under a lot of osmotic pressure and too much water is flowing in or something else like that. And then you're not interested in knowing if it's just anisotropic. You want to know how pancake-like it is. You want to know how this middle dimension fits between them because that's actually the metric you're interested in assessing. And just knowing the anisotropy doesn't give you that much information about your object. Particularly in fields like material science and mechanical engineering, these shapes are quite important because if you look at the forces that are created by having holes that have these shapes, the forces or the force distribution around a pencil-shaped hole and the force distribution around a plate or pancake-shaped hole are very different. And so if you're looking at how this hole affects the integrity of the structure or how a cell inside of this hole might sense the forces around it, knowing where it fits on this scale is quite important for modeling that accurately. And so the term we use to quantify this is oblateness. And so what oblateness looks at is basically these eigenvalues that we had before, and it looks at the difference between sort of the second and the first dimension and the third and the first dimension. And so basically it gives you where is your middle dimension on this axis between the first and the third, because it has to be there somewhere. We know that these are ordered correctly. And if it's a -1, this indicates that the object is sort of the same length as the shortest semi-axis. And this would be then a prolate or a pencil or rod-like object. If it's then +1, then the middle axis is the same length as the longest semi-axis, and then it's pancake, plate, or oblate. And so this metric then allows us to see how those objects change shape as you go between this sort of -1 and 1, and quantify these different shapes which have exactly the same anisotropy. So now, to kind of look at interface and surfaces. And so many of physical and chemical processes occur at surfaces or interfaces, and it's very important to sort of define and understand what these are and how they look. And so it's something we'll go into in more detail in the next lecture, but we'll talk about it a little bit now. And so we have this idea of kind of segmenting volumes and areas. And so if you have a 3D image, you segment out a list of pixels, which is a volume. And if you segment a 2D image, then you have all of these areas. And interfaces are sort of by definition one dimension lower. And so in 3D objects, you're looking at surface area. And in 2D objects, you're looking at perimeter. And so these interfaces are quite important for looking at sort of connectivity of cell networks. So for neurons, if you're trying to understand how they're connected together, it's very useful. For material science processes, and so if you're looking at like a foam or a liquid metal, understanding how this structure coarsens with time, you need to look at the surface areas because those are the kind of driving factors in this coarsening process. And for chemical processes, if you're looking at things like surface-bound diffusion or catalyst actions, it's very important to know how much of these surfaces are exposed, for example, to where this substrate might be flowing through, and how the surface looks. And so a surface that's very small and flat isn't going to interact very much, and if you have a surface that sort of has lots of ripples inside of it, it's going to have much more opportunity to react with the things that are coming by. And so we can actually calculate or estimate this with these morphological tools that we developed before. And so does anyone have any idea of how you would do that with erosion and dilation? How you might be able to estimate circumference or surface area? So not circumference, perimeter. No idea. Does anyone have any idea how you'd estimate surface area at all? So if you have a sphere, I mean, you know that the surface area is 4 pi r cubed, pi r squared. But if you have an object that's not a sphere, how would you calculate the surface area? Yeah. Yeah, so you can do triangulation. What's an even simpler way of doing it? Yeah, you can add up the voxels, and that gives you the volume. Yeah, so if you look at the voxels that are exposed to the outside, or the pixels that are on the border, you can calculate how many of those faces are sort of exposed. And you get a very rough approximation for what the surface area might be. That's right. And how might dilation or erosion help you with this?
You can see how much it changes to make sure there's no loops inside.
Right. So you look at how the volume changes when you dilate and when you erode, and you get a fairly accurate estimate for the surface area. It's not as accurate as doing sort of this triangle or marching cubes-based approach, but it's a fairly good approach. So you can look at what's the volume you have when you do one erosion, and what's the volume you have when you do one dilation. And then you do the difference of those volumes, and that gives you an approximation for what the perimeter of your object is. Of course, with very small objects, it's not very helpful, because if you just have one pixel and you do an erosion, it disappears. But once you get into larger objects and the size of your object is very large compared to the pixels you're looking at, it's a fairly accurate representation of what you have. And so that's actually where these morphological operations are most useful, is when you're trying to find boundaries or interfaces, that these are very efficient ways to figure out where those interfaces are in what otherwise could be a very complicated process. So if you think about your object, if you try to find where does this border this, you have a searching problem, and you have to go through all the points in your image and try to see, is this bordering this, and look at all the neighbors, and it would take you a very long time. And what's nice with morphological operations is that they're implemented very efficiently. And so you can use these operations to find these interfaces or find these perimeters and areas very quickly, because you know that these operations work very efficiently. So you don't have to re-implement everything yourself and have it work well. And so here we know, because this is a model image, what the circumference should be. Of course, that will never be perfect, because it's being represented, you're trying to represent a circle by pixels. But we see this radius and the model circumference versus the morphological estimation, and they match up fairly well. Meshing is then sort of this idea of taking triangles or trying to come up with sort of a better representation for these images. And so once you've segmented the image, you have a kind of pixel-based representation of your image. And if you have here, for example, an experiment where you were compressing a block, and you have the image here before and the image here after, and you try to calculate how much deformation took place. This is quite difficult from a pixel representation of an image, because all you see are the different pixel values, and there's not really a way to quantify, or an easy way to quantify, how difficult is it to turn a pixel off. You know, in reality, if this was a material that you're compressing, you know, the cost of completely destroying a piece of material is exceptionally high. And so that's a really unlikely event to occur, and then a pixel representation isn't really matched well to the reality of the situation, because the pixels don't turn off, they move. But in this representation, you can't really see that, and you can't really bring that in. And so once you have a mesh-based representation for your object, so we're representing your object as sort of this list, this grid, rather than these on and off points, then you can look at sort of this very simple, you know, Hooke's model for a spring, where this is kind of the resting length, and the more you stretch it outside of the resting length, the more of a force, the higher force you have. And then you can see that when you do this deformation, moving these pixels or moving these points has sort of a cost in force. And then this fits very well when you're trying to then bring this back to understand the forces that are interacting inside of your material and the sort of corresponding strains that are being produced. And so that's one of the reasons that these meshes are so important, is they give you a much closer to reality model for what you're looking at. And that pixels are sort of a bad approximation for most materials. Cool. And so what you can do is, of course, the approach we just covered, where you basically take each exposed face belonging to the surface, and you build up the surface out of all of the exposed faces. This is not a very accurate representation, but there are much smarter methods for doing this. And so you can go to Wikipedia if you're interested and read all about the sort of different image-based approaches for meshing. And there's quite a few. This is just the very beginning. I think we still have. One of the most important algorithms here, and it's actually quite old, is called marching cubes. And so the idea is that voxels are pretty poor representations for surfaces because they're sort of, by definition, always have right angles at all of the edges. And so it doesn't show you very well what the surface looks like. And particularly if you're trying to look at things like curvature, in a voxel-based representation, you either have a sort of 90-degree corner or you have a flat surface. And so your curvature is either very, very high or almost infinite or zero. And so if you're trying to calculate curvatures on much larger objects, that's not a very helpful representation for what your object looks like. And so what the marching cube approach lets you do is it lets you go through your image kind of one voxel at a time. And again, this is implemented very efficiently, so even though it sounds very time-consuming, it happens very quickly. And it looks at the neighbors of those voxels and decides which sort of face represents this combination well. And so if you have sort of a bunch of points that are on a diagonal line, it will then represent that as a flat surface rather than representing it as a bunch of stair steps in this line. There's also sort of the successor of marching cubes, which is called marching tetrahedra, which then does this over a larger scale with more complicated shapes. And so this allows you to represent some of those structures even better and match it better to kind of what systems you're actually looking at. Cool. So if we look at what sort of things we'll cover next time, we'll have we'll look at how we can analyze these images in even more detail, and particularly this case here, which is fairly frequent in imaging. And so here we see that the bounding box was not a very good approximation, but the ellipse was also not perfect, because what we probably had here, with sort of an understanding of the system, is three cells that were sort of too close together. And so we want to be able to identify that those are in fact separate cells and kind of divide it and understand how each of these cells looks differently. Or if we say that this is one cell, how can we understand the shape that it has better? So we see that it doesn't fill the bounding box well or the ellipsoid well, but how can we quantify sort of, what's the radius of curvature inside this feature, and how can we get more metrics out of it that characterize this sample well? So that's it for this lecture, unless there's any questions.